Good morning. Today, I'd like to talk about an integration technique called integration by parts. First, I need to establish the premise. We're going to have an integral that we want to do. This integral may have several factors multiplied together in the integrand, the thing that we're integrating. So, for instance, here, I'm thinking sort of generically as integral of a of x times b of x times c of x times d of x times e of x with respect to x. D of x is a function value of the d function, not to be confused with the differential dx down at the end. Depending on what these factors are, it's possible that I can rearrange them in some way as to make life easier on myself. For example, depending on what these functions are, it might be advantageous to group the b of x times c of x times e of x together and group the a of x times d of x with the differential symbol together. We might call the first function of x u, and this second thing, which is a function of x dx, we'll call dv. So generically, we will have a way of splitting our set of factors up in this way. The hope is that by writing it this way and taking advantage of a fact that's related to the product rule, I may be able to get an integral that's easier to do than the first one. In what follows, I'm going to think of u and v as being functions of x. I really should write u of x and v of x, but to keep the writing under control, I'll just write u and v instead. The product rule says that the derivative of u times v is u times the derivative of v plus v times the derivative of u. On the other hand, if I know that the derivative of that is that, I could integrate both sides and turn it into a new statement. Doing so, if I find the derivative of uv, and then I find the antiderivative of that, I end up with u times v. Really, u times v plus a constant, but as usual, I'll wait till the end to put the constant on. Over on the right-hand side of the equation, I am integrating with respect to x the sum of two things, so I can think of doing the integrals separately. And here's a key point. When we do integrals by u substitution, we have something very similar to what we're writing here. We refer to the derivative of v with respect to x dx as just being dv, and likewise for the u. If I write it that way, what we have written down here says u times v is the integral of u dv plus the integral of v du. We'll subtract this term away from both sides and get what's called the integration by parts formula. So our result for the moment is this. The integral of u dv is u times v minus the integral of v du. And what we're hoping is that this integral is easier to do than that integral was. If we can do this integral, we will have our answer. Here's a very bad choice for u and v. I'll let u equal e to the x and dv be the rest of the factors, the x and the dx. The derivative of u with respect to x is e to the x, du is e to the x dx. dv is x dx, dv dx is x. v is an antiderivative of x, which is 1/2 x squared, since I'm ignoring the constants for now. U times v, I'll take this quantity and multiply it by that one, minus the integral of v, which is 1/2 x squared, times du, which is e to the x dx. This statement is true. This last thing that I wrote down is equal to the integral of x e to the x dx, but it didn't go the way I was hoping. The integral that I have left to deal with here is actually more complicated than the thing that I started with. I don't know an antiderivative for x squared e to the x. This is why this is a bad choice. A comment. I just noticed that I didn't have my noise suppression filter on, so I've just activated it. It'll be an interesting experiment to see if it makes any difference in the audio quality. Returning to our problem, a much better choice is u equal x and dv equals the rest of it, e to the x dx. du dx is 1. Treating these as fractions, even though they're not, du is 1 times dx. On the other hand, dv is e to the x dx. In the same way, dv dx is e to the x. V is an antiderivative of e to the x, one of which is e raised to the x power. U times v minus integral of v du turns into this expression, and the remaining integral is easy to do. An antiderivative of e to the x is e to the x. Having obtained an antiderivative for x e to the x, add a constant of integration on. If I thought it made it look nicer, I could group those first two terms together and write it as the number x minus 1 multiplied by e to the x. I'm just going to leave it like this for now. Since this is a new technique, it's useful to make sure that we've got the right answer. If this is right, then the derivative of this quantity must be x e to the x. If I calculate the derivative of my answer and it doesn't come up x e to the x, then something has gone wrong on me here. I'll disregard the constant of integration because the derivative of a constant term is 0. For this part, I'll have to do the product rule. First function times derivative of e to the x times e to the x, plus the derivative of the first function, which is 1, multiplied by e to the x, minus derivative of e to the x is e to the x. Those terms cancel out, leaving x e to the x behind. So this is correct. This is the right answer. For my next example, I'd like to integrate x cosine x with respect to x. I have things multiplied together. Since this isn't on my list of things I know how to do, my first thought is, how about this new technique we've just started talking about? I'd like to think of this as the integral of u dv, where I'd like the derivative of the u to be no worse than the u was in some sense, no more complicated, and yet at the same time, I want to be able to integrate dv dx and figure out what the v is. Even if I can do those two things, there's no guarantee that I can do the integral that I get at the next step, but we have to deal with that when we get there. In view of what happened when we made the bad choice on the previous example, I know that I don't want to let dv be x dx because that'll make the integral more complicated instead of less so. If this plan has a chance of working, I should probably make u equal to x. Then the derivative of u is a constant. Du equals dx. dv needs to be the rest of it. dv dx needs to be cosine x. V needs to be sine of x. As always, save the constant of integration for the end. The integration by parts formula is u times v, x times sine x, minus the integral of v du, integral of sine x du is dx. The desired thing has happened. This new integral is easier to do than the original integral was. An antiderivative for sine x is negative cosine x, so we will have x sine x minus the negative of cosine x, that is, plus cosine x, plus a constant of integration. Just as before, it's not hard at all to check this answer. I'm going to differentiate my answer and see if I get x times cosine x like I'm supposed to. I'll have to do the product rule here. The derivative of the answer is x multiplied by derivative sine x, x times cosine x, plus the derivative of x multiplied by sine x, 1 times sine x, plus negative sine x, plus the derivative of a constant is 0. These terms cancel each other out, and all that remains is x cosine x, just as it should be. To end this introductory video, I'd like to look at one more example that's a little bit more complicated. I'd like to find the integral of the quantity 3x squared plus 5x plus 1 multiplied by cosine x. In view of our preceding comments, it ought to be pretty clear that I ought to make the u equal to the polynomial. Letting u be 3x squared plus 5x plus 1 and dv, the rest of it, cosine x dx, getting our hands on du and v is done very similar to how we did before, and the integration by parts formula gives you this. In view of what I'm going to do in a moment, I'm going to write sine of x times 6x plus 5 as 6x plus 5 times sine x. There's good news and there's bad news. The good news is, in the integration by parts, we're able to get our hands on all the required quantities. The bad news is, this is not on our list of things that we know how to do. There's also sort of medium news, though. The original integral had a quadratic polynomial times a trig function in the integrand. After doing integration by parts, I now only have a linear polynomial, first degree, times a trig function. The new integral is not on my list of things I know how to do, but it is simpler than the one that I started with. So an obvious thought would be temporarily forget what I've been doing here and just pretend that somebody told me to evaluate this integral. I can probably do it using integration by parts. Once I've got that in my hand, I will take whatever the answer to this integral works out to be and subtract it from that, and then I'll have my answer. So what I'm going to do is I'll write this down. I'm going to subtract something away from it. This something is whatever the integral of 6x plus 5 sine x with respect to x works out to be. I'll try to get this new integral using integration by parts again. It's important to understand that the u and the v that I'm about to write down have very little to do with the u and the v that we were talking about previously. So letting u be 6x plus 5, the derivative of u with respect to x is 6, which is good news because 6 is a constant. Du will be 6 dx. Meanwhile, dv being sine x dx means the derivative of v must be sine x. V needs to be an antiderivative of sine x. Negative cosine x will work. Notice that you have to be very careful about your parentheses and grouping symbols. U times v is the number 6x plus 5, that number, times v, which is the negative of cosine x. Then I'm supposed to subtract away the integral of v du. V is negative cosine x, and du is 6 times dx. Minus minus is plus. Bring the 6 out front. We started off with an integral that had a quadratic times a trig function. We did a step of integration by parts and got something that had a linear function times a trig function. We did another step of integration by parts, and now, if I know an antiderivative for cosine x, which I do, we'll be in business. An antiderivative for cosine x is sine x, because the derivative of sine x is cosine x. This is the integral of 6x plus 5 multiplied by sine x dx. This is what I'm supposed to put inside the brackets here. There's going to be some more of this. Minus minus is plus. Also, I will have minus 6 times sine x, which I will eventually combine with this first term. Then, adding on the constant of integration, I'll be done. If I group together the terms that have a factor of sine x, I will have 3x squared plus 5x plus 1 minus 6 multiplied by sine x. That is to say, 3x squared plus 5x minus 5 sine x, the 6x plus 5 cosine x term, and then the constant of integration. If I've done all of my calculations correctly, the derivative of this ought to be the thing that we started off with, which is 3x squared plus 5x plus 1 cosine x. As usual, I'm going to check this, but notice this time I'm going to have to use the product rule twice because both the first and second terms involve products of functions. Observe from the first product rule, from that one, I have a term that is 6x plus 5, that number, multiplied by sine x, while in the second product rule, I get a term of minus 6x plus 5 sine x. That term and that term cancels each other out, so I'm not going to write them down anymore. Also, in the two terms that remain, both have a factor of cosine x. So finally, having done all the algebra, the derivative of my alleged answer is 3x squared minus 5x plus 1 multiplied by cosine x, which is what it's supposed to be. So 2 applications of integration by parts, being very careful about the plus and minus signs and the grouping symbols, has produced the correct answer. For some odd reason, my video editing software has chopped off the very end, so I'll just say, coming soon, we will look at some other examples of this integration by parts business, and until then, I hope everybody has a good day, and I'll talk to you again soon.